मैंने उसमें कॉपी करके रखा था, मिटा दिया। अच्छा, अभी तो ऑफ है ना सर? ऑन है सर? नहीं नहीं, ऑफ करो। ये वीडियो भी ऑफ कर दो, स्क्रीन भी ऑफ कर दो। ये हाँ, because it will not be projected there.
Yes, sir, that is what I mean. They said the faculties have requested. I don't know.
अच्छा, ठीक है।
So I can, may I just attend to my lab only?
हाँ, अच्छा, अपना आपका नंबर दे दीजिए, बाई चांस अगर डिस्कनेक्ट हो जाता है तो फ़ोन कर दूंगा आपको। हाँ, 1 टका लिख के पेपर में ना अपना नंबर लिख दीजिए। हाँ, कितना लोग हैं पता करने के लिए क्या करना पड़ेगा?
इसको क्लिक कर, उसी को
इसी को।
हाँ जी सर।
अभी सर है
99।
कुछ चैट कैसे करते हैं?
ये सर ये वाला है।
ये वाला?
हाँ।
अच्छा, रिकॉर्डिंग इज ऑफ। अच्छा, हाँ, एक मिनट। अगर यहाँ से मुझे चैट में जाना है तो क्या करना पड़ेगा?
वही उधर से कितना
ये
हाँ जी सर।
फिर ये वाला ना, ठीक है। 12 नहीं होगा 11 Good morning, everyone. Can everybody hear me?
Yes, sir. Yes, sir.
Okay, we are starting the class then. So this was supposed to, this is again a lecture class on enzymes. In my last class, if you recollect, I had talked about the thermodynamic principles of chemical reactions and how the delta G zero a chemical reaction, whether a chemical reaction will depend on will happen or not depends on delta the free energy change, and it has to be negative, and the difference between standard free energy change and physiological free energy change, as well as the free energy change of a particular reaction. Okay, and also we had talked about that all chemical reactions usually take place in the presence of one or multiple transition states. So like in this example, in this we have, say, glycerol 3 phosphate converted to dihydroxyacetone phosphate, and there you have a transition state. In this case it is more stable, and that is why it can be easily measured, and that's why I have used this as an example. In most of the in most of the catalytic reactions, the transition state is not very stable, is metastable, and hence it is often very difficult to measure. And as we see that the free energy change of glycerol 3 phosphate is about at this, if it is at this point, and the free energy of this is around here, so this reaction should spontaneously be carried on. But what happens is that it is never a spontaneous, even though there is a negative free energy change, because this transition state analog is at a higher energy than this. So that means this transition state has energy which is higher than the substrate, as well as definitely about the product. So we see the transition state, which is in this case is cis-enediol, is at a higher state, free energy state, than the substrate, which is glycerol 3 phosphate, or the product, which is dihydroxyacetone phosphate. Now remember that here you see I have put a double-sided arrow. That means the reactions can take place either way. But here you see the transition state has a higher free energy and than the substrate, and the substrate has a higher free energy and the product. So the question naturally arises that how can this product, this free energy of this product, can be converted to the substrate to make it a reversible reaction. The point behind this is, the reason behind this is that the transition state, what we are seeing here is the standard free energy change. That means where the initial product concentration was 1 molar, and then after equilibrium they will have a different molar concentration, and it is based on that. But however, as we have seen before, in this case, but the net free energy of a reaction depends not only the standard free energy change, but also on temperature, as well as the concentration of the product upon the concentration of the reactants. So even if this is a negative thing, if you can increase the concentration of the product to a much higher level, then this whole factor will become much more positive so as to overcome the limit set by this negative standard free energy change, and hence the net free energy of this whole reaction might be positive in the forward direction, and similarly it will be then negative in the reverse direction. So by changing the concentration of the product and by playing around with the concentration of the product, like means if this product is rapidly siphoned off to another chemical reaction, or if the preceding chemical reaction produces a lot of this substrate, the free energy change, the directionality of the reaction can be altered without coming in conflict with the laws of thermodynamics. Okay. Now, and as I said that even if you keep this glyceraldehyde 3-phosphate in a test tube in a solution in a test tube on the table, some amount of it, because in this direction it is favored because of a free energy change, some amount of it will be converted to dihydroxyacetone phosphate. But then that will be very slow. Why? Because the total net energy of the molecules of the glyceraldehyde 3-phosphate is distributed and as a sort of a Poisson distribution, which is which almost becomes similar to a normal distribution. What happens is that in Poisson distribution, here it touches the x-axis, whereas in the other direction it barely touches the x-axis. That which means that some molecules will have a net some amount of energy, minimum amount of energy, and some will have higher amount of energy. Now what happens is that these molecules, by internal collision between them, as a result of Brownian motion, will acquire some energy changes. So a molecule which has a free energy level of around here might, by bouncing or colliding elastic or inelastic collisions, one molecule can slowly acquire a higher energy and then reaches in this part, and as it reaches this part, it has reached the energy of the transition state, from where it can also form the product. So this is the principle behind the spontaneity of reactions, but this will be very low, because you see, if suppose that these number of molecules are at an energy of higher transition state, so only this, of all the substrates that are present, only these molecules of the substrate will have the capability to form the product, because they are at a higher energy state. Now coming to the enzymes. Now what happens is that the enzymes they are basically catalysts, biological catalysts, and can be and they help to stabilize the transition state analog by the different side chains of the amino acids interacting with the substrate in such a way that some bonds are weakened and some more bonds are formed. Okay. So what happens if this is the transition state of cis-enediol, if that is being stabilized by these chains, side chains of the enzyme, what happens? This transition state has a lower free energy. So you see, the free energy of the reaction in the presence of enzymes of the transition state, the free energy of the transition state is lowered, but ultimately you see the free energy of the substrate and the free energy of the product does not change. So what happens basically in an enzymatic reaction? The enzyme first binds to glyceraldehyde 3-phosphate to form an enzyme glyceraldehyde 3-phosphate molecule transition state. Now this, so it binds here, and then what happens? This proton from the histidine side chain is donated here, this proton is donated here, resulting in the form of a single breakage of a bond and forming a single bond here, as you see here, and because of a double bond is formed here. So this by itself, if you look at the previous thing, it is the same thing what is happening, but now this this formation of these bonds and breaking of certain bonds are now stabilized by the enzyme substrate complex, and that lowers the free energy of this molecule, the intermediate. So the number of molecule, the free energy of the reaction which is catalyzed by the energy with the transition state molecule of the reaction which is catalyzed by the enzyme has a lower free energy. So, and then the bonds are again it goes another transformation where this proton is donated back to this histidine group, and so is this proton from this group, and ultimately it forms the enzyme product complex. And then once that happens, the product leaves the enzyme, leaving the enzyme molecule unchanged. So now what happens? You see, thermodynamically, since the transition state of the molecule catalyzed by the enzyme, of the reaction catalyzed by the enzyme is lower. So what happens thermodynamically? At this level, there are more number of molecules that are present. Previously, if you see at the original level, only this much, for example, this much molecules were at a higher energy state which can easily form the substrate. Whereas now we see here at this energy state, there are more number of substrate molecules are present, so they can easily convert to the product, which means that without changing the directionality of the reaction, the enzymes do not alter the directionality of the reaction. They equally affect both the reversible as well as the forward reaction, but the number of molecules at the transition state or higher, at the transition state energy or higher, is much more in a catalyzed reaction, especially also in a enzyme catalyzed reaction, and hence it can lead to an increased rate of reaction just because there is more number of substrate molecules at a higher energy. Is it clear to everybody? Hello?
Yes, sir.
Okay, fine. So now what I have said is, for example, if basically what is happening in a non-enzymatic thing, the free energy of this molecule is about here, and this molecule is about here, and the product is here. So you see the free energy of this molecule is higher than the free energy of either this or the substrate, a product. Now we are considering here that there is only one transition state. In enzymes, in many reactions, there can be multiple intermediate steps, because some amounts, for example, once this bond is broken and a proton is got from the media, then that will be one intermediate reaction, intermediate transition state. So there can be multiple transition states. So you see, this is the transition state of this stable intermediate molecule, but before that there will be much more, and after that also there can be many more, one or more intermediate states. So that intermediate stage, when only one bond has broken, for example this has broken and it has taken our protein, that is much more unstable, but that can have a higher transition state. So do not think of that chemical reaction goes on because of just one transition, by the means of one transition state. There can be multiple transition states. Like here, as I had mentioned, you have one transition state which is an intermediate between this original substrate and the stable intermediate, and there can be another intermediate between this and this again. And what happens in a enzymatically catalyzed reaction, do not think about this mutant and all those things, just think about, take this example of this one, the red ones. Don't worry about the blue here. the enzyme substrate complex will have a slightly higher free energy, and then it forms another intermediate. Then again it forms this intermediate along with the enzyme, so which has a higher free energy transition state analog, but it's definitely lower than the uncatalyzed reaction. And that way you have the transition states of each and every step in a chemical reaction is lowered in the presence of enzymes or catalysts, and hence more number of molecules will be available at this energy level to be converted to the substrate, to the product. So we see though it starts off with the same free energy at the substrate in all the reactions and the same free energy of the product, the intermediate transition states, multiple transition states are there, and all the transition states energies are lower than an uncatalyzed reaction, and hence this reaction is hastened. So the enzymes basically do not alter the chance of a reaction, it just increases the rate of the reaction. So if the enzyme is reversible, so the reaction, if the reaction is reversible, then the enzyme will catalyze both the forward and the reverse reaction at an equal rate. So okay, now we will have to consider a little bit about the rate of the reaction. Since we say that reactions the reactions that are carried out, enzymes catalyzes reactions and they change the rate of the reaction. So we have to consider a little bit. I will not go into the details of the calculations, but you have to understand a little bit that how the mathematical treatment of how enzymes change the reaction velocity. For example, in an uncatalyzed reaction, say this we are talking about an uncatalyzed reaction, or maybe you can take a catalyzed reaction also. A is being converted to B. So what is the velocity of the reaction? That is basically rate of production of increase in concentration of B over time, and or rate of decrease of substrate concentration over time. So V, or velocity of the reaction, is the differential of the concentration of the product against time, or negative differential of the concentration of the substrate against time, and this will have a value which is, say, K1 into the concentration of the substrate. So if you take this, the disappearance of the substrate as this thing, so as a measure of the velocity, what happens is differential of A against the concentration of A, differential of concentration of A is equal to minus a reaction constant upon with dt. And now if you, what is the total amount of reaction that is being formed? So if you integrate this between the original concentration and the concentration at a certain point of time, it will be something like this. Integration of this whole between within the limits of original concentration of the substrate and the concentration of the substrate at a particular period of time will be some like this. And hence we have, if you solve this, so you do not have to do not have to understand how this is being solved, because that will not a part of your curriculum. But solving this integral equation, it comes to that log natural of the concentration of A at a particular time upon the original concentration of the substrate is equal to minus K1T, or this is the final. If you take the antilog of this, so this is the ultimate result. The concentration of the substrate at a particular period of time upon the concentration of the original concentration of the substrate is equal to e to the power minus K1T. Now if you plot this, or it comes out, it boils down to this equation, that concentration of of the substrate at a particular time in a reaction is equivalent to the concentration of the original concentration of the enzyme into e to the power minus K1 into T, minus K1 is the forward rate constant. So if you plot it, If you plot this equation in a form of a graph, you will get a logarithmic plot where you see it decreases like this. So, with increasing time, because the reaction is going on, the concentration of the substrate at any particular time is decreasing in a logarithmic form. So, if you plot it in a logarithmic scale, you will get a standard straight line, which means that at each point you see the velocity of the reaction is changing. Why? Because this was at this particular point, when it was much steeper, there were much more number of substrate molecules. So, more number of substrate molecules means more number of molecules can strike against each other to get into a higher energy state, to reach the transition state, and so more number of molecules will be converted to the product. But as the reaction goes on, the substrate is being utilized, so the concentration of the substrate molecules decrease. So, there will be less molecules in substrate molecules in the mixture, in the reaction, to strike against each other, to form new bonds, to go to a higher energy, and hence the net. So, the number of molecules at the transition state will decrease. Number of substrate molecules at the transition state will decrease, and slowly the rate of the reaction will go down. And that is why when you measure enzymatic activities, for example, in your clinical classes, in your clinical chemistry, you will be dependent on measurement of various enzymes in the body that are being produced in excess amounts during, say, disease, or less amounts in diseases. When you have to measure that in any enzymatic activity, you have to be very careful to have the substrate constant, say substrate concentration, to be not limiting, because as the reaction proceeds, the substrate concentration becomes limiting. Now, if you are measuring the enzymatic activity over a period of time, you have to see that the substrate concentration does not fall to very low levels. So, initially for all enzymatic estimation of enzymes clinically, the initial starting concentration of the substrates has to be high, because within the period of the measurement, the substrate concentration should not fall so as to lower the change of the enzymatic activity. So, continuing with that, as I said, in the previous we considered it is a unidirectional enzyme, but it is a reaction, which is not true. It actually happens is that most of the reactions in our body are reversible. That means they can go in the forward direction or they can go in the backward direction. So, if the forward rate constant or the rate of the forward reaction is K1, which means the velocity of the forward reaction is the decrease in the concentration of the substrate upon differential with respect to time, and that is, as we learned previously, it is equal to minus K1 into concentration of the substrate, and the reverse reaction, the B becomes the substrate, this becomes the product. So, the rate of the reverse reaction is the negative of rate constant of the reverse reaction, that is K upon minus 1 into the concentration of the substrate here. Somebody asked a question whether all of them are first order. So, for sake of simplicity, I am considering that the reaction is a first order. Most of the reactions in our body, many of the reactions are first order. That means there is only one substrate and one product. But unfortunately, there are many reactions which are also have multiple substrates. Now, we will see later on that a multiple substrate enzyme reaction may not be simultaneous. That means A plus B plus C is not giving D directly. What will happen? A plus B will first react to form an intermediate with, say, X. That X will react with D to form the X will react with C to form the compound D. So, most of them are either first zero order or first order, or second order. Beyond that, in the biological systems, we do not require, we do not study, we do not find, we do not have much examples of higher order reactions, 0, first and second order. But I am limiting to only first order, basically because the mathematics behind it is simpler for you to understand and for me to explain. If you go for a higher order reaction, then the mathematical treatment of this becomes very complicated. So that's why I am sticking to myself to only first order reactions. Is it clear to everybody? Somebody made another comment. I could not catch it. Actually, how to? Okay. There was some other comments.
In front of K1 and K minus 1, there shouldn't be a negative sign.
Where? Which one?
Sir, V forward, velocity forward is equal to minus K1A. I think that's incorrect, and it should be velocity forward is equal to K1A. Minus dA by dt equal to K1A.
No, because we are talking about this one. Because the disappearance of the substrate, we are measuring the velocity of reaction not in the form of formation of product, but the rate of disappearance. So if you are talking about V forward is equal to Vb by dt, then it will be a positive, because this part is
Minus
yes.
dA by dt should be K1A.
But I don't know, because this is what I have been I know.
Sir, can we go to the previous slide?
Yes.
Yes, sir. In the first line, minus dA by dt.
Okay, sorry, yes. Maybe I made a mistake here. So okay. Okay, thank you for pointing this out. Okay. So V forward is equal to K1 into A, and the reversible reaction rate will be K minus 1 into the concentration of the product, which is the substrate in this case. Now at as the reversible, in a reversible reaction at equilibrium, the velocity, net velocity is 0. So basically V forward is equal to V reverse. So at concentration, the concentration of the product upon the concentration of the substrate is this, which is the K, which is known as the equilibrium which measures which is basically the equilibrium constant. Okay. Now what happens in basically a reaction we are talking about? Now we will now study the rate of the reaction in bringing into account the transition state concentration. Okay, so now we break this A and B to a third. We bring a third molecule, which is the intermediate molecule, which here in case means the A double plus. Okay, so now the forward reaction is basically how many molecules are going to the transition stage from the substrate, and the reverse reaction means how many molecules from the product stage is going to the transition state, going back to the transition state, because the number of molecules in these regions, they determine which if more number of molecules are going from this stage to this, that means the reverse reaction is now being favored. If more number of molecules are going from here to here, the forward reaction is being being favored. So now we bring the K1 and K minus 1 we differentiate between only these two on these two different sets. Like for example, K1 will be equivalent to is a concentration of the intermediate upon the concentration of the original of the substrate, which in thermodynamic terms is equivalent to this if you remember from your class 12 classes and as well as my first or second slide, is this. So what happens then, if since the enzymes are causing a decrease in the free energy change, for the previously the uncatalyzed reaction has a free energy change of this much, which is now being shortened to this much. So the free energy change of the reaction of this part of the reaction only, remember I am not talking about the whole reaction, only this part, which is decreasing. If this is decreasing, then this will be increasing, and hence this more number of intermediates will be increasing. Okay. And that is reflected by this equation, where why it is decreasing, because it is decreasing by this which I am saying as delta GD in the presence of an enzyme. So original delta G of the reaction, of the forward reaction, minus the decrease in the delta G because of the enzymatic, the transition state decrease due to enzymes, is this. At the same time, since this, so and now let us come to the backward reaction. The rate of this reaction will be dependent upon, again the rate of this reaction will be dependent upon the product concentration upon the transition state concentration upon the product concentration. And again, hence you see that this was the net delta G in an uncatalyzed reaction, the blue one. The red one is after the enzymes are catalyzing the reaction. So we again see that there is a decrease in the reverse, the delta G between product and the transition state analog, and hence this reaction will also increase. The rate of the reverse reaction will also increase. So ultimately, if you take K1 upon K minus 1 with this, it again turns out to be equivalent to this concentration, this equation, which is equivalent to K. Is it, am I clear to everybody? Hello? Okay. Okay. So what we have seen, so at this thing, at a equilibrium, the concentration of B upon, which is the product, upon the concentration of the substrate is equivalent to e to the power, that a term which is equivalent to K. And so it is almost a repetition of the previous slide, that the K of the what we have got from this K had come from the thermodynamic calculations, where we did not look at, if you see, remember my first slide, let me go to my first slide, this reaction, basically this one. Okay, so this was arrived by, this slide shows the derivation from that formula that I have shown just now. Now if we and in the previous slide what we had shown, this was arrived by the studying the velocity of the reactions, and ultimately, so you see the rate constant that we can arrive by this formula using the velocity reactions is ultimately is convertible to the original formula that we can arrive by the thermodynamic principles, by working through thermodynamic principles. So this brings an end of today's thing of calculation of studying the velocity of the reactions and of velocity of enzyme catalyzed reactions. Now we will move to the main enzymes now. Now there you see our body has lot of enzymes in our system which catalyzes innumerable reactions that are important for carrying out the basic functions of life. Now enzymes can be classified, broadly classified into 6 categories depending upon what they are catalyzing. It can be either oxidoreductase, transferase, hydrolase, lyase, isomerase and ligases. Now what do you mean by oxidoreductase? Which means they catalyze oxidation reduction reactions, which means either transfer of hydrogen or oxygen atoms or electrons from one state to another. And these are some of our typical reaction examples of typical reaction where this hydrogen is donated from one molecule to another, giving rise to this molecule being reduced, and this molecule, since hydrogen is moving away from this molecule, is oxidized. Same with direct oxygen, where they are oxidized directly. So that is why this category of enzymes are known as oxidoreductase, because when one molecule is being oxidized, other molecule is being reduced. The second category of the second category of enzymes that are there that has been categorized is category number 2, which is called transferase, where a functional group from one substance to another is being transferred. So that group can be anything, a small group, methyl, acyl or whatever phosphate groups. And so these are basically enzymes that transfer one group from one substance to another are known as transferases. Hydrolases is when one molecule is broken in the presence by water molecule. Remember, water molecule into two separate molecules or cleaved by a water molecule. This AB is cleaved by the water molecule into two different molecules, and that is known as hydrolase, because water is being used to cleave the molecule. And that is the difference between hydrolase and lyase, where it is lyase, as the name suggests, is breaking, which means bonds are being broken, but where water is not required for the reaction. Then the fifth category is isomerase, where there is an intramolecular rearrangement. And the sixth category is ligase, where two molecules are joined to form a new molecule with simultaneous breakdown of either ATP or any other high energy molecule. So on the whole, all the enzymes in the universe have been classified into 6 broad categories: oxidoreductase, transferases, hydrolases, lyase, isomerases and ligase. Now you see, I have written a term called EC in front of 1. Now this EC stands for Enzyme Commission. Now to classify all these enzymes, there is a commission. Now this commission has a nomenclature which is equivalent to the different version nomenclatures that you see in softwares, say version 2.1, version 3.4, something like that. Okay, now so actually each enzyme can be classified by this enzyme commission method into 4 parts. So you have, just like in software, you have version 2.1 or something, you can have EC or enzyme commission number 3.4.11.4. So there will be 4 digits that can classify each and every enzyme that is existing in the universe based on this following principle. Like the first one, which shows the broad category of the enzyme. We are here EC3, so it is a hydrolase. So you then the second number catalyzes is that what bonds are being acted upon. So this particular enzyme acts upon peptide bonds. So this 4 comes. So for different types of bonds that are being hydrolyzed, this number will change depending upon which bonds are you talking about. So the second digit in the enzyme composition number denotes the bonds that are being hydrolyzed. The third number denotes what is the substrate. Sorry, what is the product, ultimate product, which means that in this case the product is the amino terminal amino acid from a polypeptide. This tripeptide aminopeptide is. So amino terminal amino acid from a polypeptide is the product. And what is the substrate? That tripeptide is the substrate. So by these 4 numbers you can know what is the type of enzymes that we are talking of, what is the nature of the enzymatic activity, which is lyase or ligase or hydrolases or transferase or oxidoreductase. The second number shows what bonds are being broken. What bonds are being broken. The third number denotes what is the substrate. Sorry, what is the product. And the fourth number denotes what is the substrate. Is it clear to everybody now? Am I clear? Okay. So to continue with this example, like to continue, you do not have to remember anything beyond the first digit. Till the first digit is very important for you, because you have to know what is the type of the enzyme, what does it do. Just to clarify the second digit, that what are the type of bonds. For example, in this, if it is 4, means it is a lyase, EC4. 0.1 means it breaks the bonds. What type of bonds it will break? The carbon-carbon bonds. The next point is, what is the output? It can be a breaking of it can be aldehyde, decarboxylase or others. If it was a carbon-oxygen bond is being broken, then it will be 4.2. If it is a carbon-nitrogen bond is being broken, it will be 4.3. Similarly, for different types of molecules bonds that have been broken, it will change. And the 99 number is reserved for anything that cannot be that is not within this list of bonds that are standard bonds. Now you will wonder, why go to all this trouble to name an enzyme, to classify an enzyme? This is required. You do not need to, you as physicians or as medical students do not require to remember all these numbers except the first number. What is the broad type of the enzymes that you are talking of? The rest are important for various purposes. Like suppose you have to engineer, you have to say break up a biomolecule into 2 parts, and you have to look for an enzyme. Which enzyme will you use? So now you know the molecule, biomolecule. You know what you have to do to that biomolecule, whether you have to oxidize it, reduce it, break it, or whatever. So your idea is to look for an enzyme that will do that job. Now, so by the first number you can by deciding what is your purpose with that biomolecule, you can cleave, you can use that particular group, you can go to that particular enzyme number. Then you know, you see, decide which particular bonds are to be broken. So then you get another number. Okay. Then you see what are the products that are being required, are required from your thing, and what will be the substrate. So once for your hypothetical enzyme requirement of an enzyme, you have found out all the 4 digits. Then you can go through this directory, enzyme directory, and see which enzyme, whether such an enzyme is available for your action or not. If not, then you will have to think of other ways. If yes, you can just pick up that enzyme and use it for your chemical reaction. The number 99 is basically anything that has not come, anything which is not there in the previous list. Okay, so there can be another 4.7 here also, 4.8 for some other bonds. Okay, so number 99 is reserved for other reactions which cannot be, other bonds which are not categorized in the previous reaction. Okay. Now you will wonder why do you need to have an enzyme? Okay, you see, an example of this is in detergents. Nowadays the detergents that are used, they have lots of enzymes in them. They have peptidase, they have lipase, there are common enzymes. There are also certain uncommon enzymes which will work on non-organic grease stains, like non-organic oil stains. Okay, so now if you want to design an enzyme that will cleave a particular compound which say soils the cloth, okay, then the question that was 4.7 and 4.8, why can be, I'm not clear. Can you repeat that? Can you again write it out, please? I cannot get hold of.
Sir, it is written that lysis can be further classified into 7 subclasses. So if we will also include 4.7 and 4.8.
No, I have not given it as an include. No, I have written here as 7 subclasses because there can be 7 types of common physiological bonds that are being broken. Okay, but there can be others also. Like here I have given an example of ferrochelatase, where it is breaking the bond between the heme and the ferritin. Iron. Okay, so that bond is very uncommon. So that is not listed in the previous bond, so it is given here as 99. Okay.
Thank you.
Okay. Basically, you see, I have 2 more classes with you on enzyme substrate interactions. Okay. Now, usually, basically, what happens is I used to have 3 classes on. Previously I used to take all the classes of enzymes. Last year onwards, I am taking 2 classes, only 3 classes: principles of enzyme actions, classifications and nomenclature of enzymes, and enzyme substrate interaction. But now I have 4 classes on that because there was some problem in scheduling because of the change of schedule, repeated change of schedule. So now in the next class, that is I think Wednesday or Thursday, I will be taking about principle of the enzyme substrate interaction. What we have learned till now is that how thermodynamics controls the reaction processes, decides the reaction process, how enzymes, we did the mathematical treatment of how enzymes alter the rate of the reaction. Now in the next classes or class onwards, we will be talking about all the how actually it happens in the system. We will try to visualize molecules in the system and how enzymes help to carry out this reaction irrespective of the mathematical treatment we have learned till date. It's clear to everybody? Do you have any other questions on this? So if there are no more questions, I come to the end of this class. In next class we will talk about different types of enzyme substrate interactions and how what happens. Okay, so thank you.
कितनी देर में आ रहे हो?